Okay, so we are talking about set along with a binary operator. So, we will just discuss some of the we will talk about group. So, this is basically algebraic structure. So, before that let us talk about groupoid. So, groupoid. Okay. So, groupoid is basically we have a group, we have a set G, let G be a non-empty set on which we have a operator star, and if star is a closure operator. So, that means if it is binary operator which is closure. So, this means star is a binary operator which is closure. So, that means what? That means if you take any two element from G, A star B will belongs to G. This is true for all AB coming from G. So, this is the closure property of A star. Then G along with this operator is called a groupoid. This is a algebraic structure. This is a algebraic concept, okay, abstract concept. This is algebraic structure. So, G along with this composition star, binary composition star is called a groupoid. Okay. So, this is the definition of groupoid. This is the definition of groupoid. We say G along with this binary operator which is closure is called groupoid. Okay. So, this is a algebraic structure. Abstract concept. This is an algebraic structure which is basically an abstract concept. So, we know the set. Now, set along with this operator together we called as a groupoid. Now, let us take some example of groupoid. Say some of the example. Z plus is a groupoid. Z is the set of integer and plus is the addition, the real number addition. So, that means plus is a binary operator from Z cross Z to Z. So, that this is closure. That means, this is a groupoid. This algebraic structure, this set along with this operator is called a groupoid. Okay. Set along with this operator we called a groupoid. So, this is an example. Even this minus subtraction, this is also a groupoid. Z, this is also a groupoid. But if we take the natural number set n and then the subtraction, real number subtraction, this is not a groupoid, because this is not a closure under this n. This is not a groupoid. Because if we take two number, this is basically minus 1 which is not belongs to n. So, this is not closure, it is not satisfying the closure property. Okay. So, there are many other example of groupoid like R plus R dot multiplication, we have Q dot. Okay. So, these are the all groupoid. So, that means, if you take this is having the closure property. Now, we define commutative groupoid. Commutative groupoid. So, we have a let G be a set, be a non-empty set, and we have a operator star on G, which is basically a having the closure property. Then it is a groupoid. So, when it is called commutative groupoid, if the star is commutative, then it is called commutative groupoid. So, this means what? This means, so the two properties need to be satisfied for commutative. First one is closure, that is for groupoid. Sorry, G. So, this is G and this is the closure property. So, this is the closure property and second one is commutative property. So, A star B is equal to B star A. This is the commutative property. So, if these two property satisfy, then it is called commutative groupoid. So, this is the definition of commutative groupoid. Okay. Now, we define associativity of the groupoid, not associativity, first we define the identity element, existence of identity element in a groupoid. Okay. So, suppose we have a groupoid, let G be a groupoid. Now, we called an element E, called an element from G obviously, identity element if and only if this property satisfy. A star E is equal to A is equal to E star A, and if it is true for all A. Okay. If we have, we take E, we operate with any other element, any element from G, it will give us the same element, and this is both the way. Now, if it is this way only, if it is A star E is A, then it is called right identity, element, and if it is E star A is equal to A for all A, then it is called left identity. But existence of existence of identity means it is from the both the way. It is from the right side as well as it is from the left side, then it is called identity element. If it is right identity element as well as the left identity element, then it is called an identity element of G. And later on we will see if such element exists, then it is unique. We will prove that theorem. So, this is the definition of the identity element. This is the definition of identity element. Now, we will define the inverse existence of inverse of an element. Okay, so let G be a groupoid. Okay, groupoid means we have only one property, closure property. We take a set, we take a binary operator, this and which is closure, then this algebraic structure set along with this operator is called groupoid. So, we take a groupoid and suppose there exists an identity element. Okay. So, this groupoid and E be an identity element of G. So, identity element exists, then what? Let A be an element in G, is A be an element in G is said to be suppose then an element A belongs to G said to be invertible. Invertible if and only if there exists an element B from G such that A star B is equal to B star A is equal to E, identity element. Okay. So, if A is called invertible if such a B exists, if there exists a B, if and only if there exists a B such that this, then this B is called inverse of A, inverse of A. Sometimes it is denoted by A star. If the operator is additive sense, then it is A minus. If the operator is in multiplicative sense, then this is A to the power minus 1. So, these are all notation depending on the type of operation we are dealing with. Okay. So, this is called inverse. Okay. Now, we define the semigroup. What do we mean by the algebraic structure called semigroup? So, this is the definition. Semigroup. We will slowly move to the define the group. Okay, semigroup means so first of all we have this G, the set along with a binary operator star will be called semigroup, is called semigroup if and only if star is closure. So, that means this is a groupoid. First of all, this has to be a groupoid and then it is associative. So, closure property. So, that means A star B belongs to G for all A B. This is the closure property, and this is basically telling us this is the property for groupoid. So, that means this must be a groupoid. This must be a groupoid, and along with the associativity property. So, A star B star C is equal to A star B star C. This is true for all A B C. Okay. So, if this is true for all A B C, this is the associativity property. associative property. So, if both the properties, so this property will give you only groupoid and both the properties satisfy, then this is called semigroup. Okay. Then this is called semigroup. So, now we define the monoid. So, we define the monoid. Okay. So, monoid means it is, first of all, it has to be groupoid. So, monoid we call this is a monoid if and only if, first of all, this is a groupoid. So, that means A star B is equal to A star B belongs to G for all A B. So, closure property, and then the associativity. So, it is a semigroup also. So, it is a semigroup also, and along with the existence of identity. So, if it has a identity element, then it is called monoid for all, this is also for all A B C belongs to G, belongs to G. So, this is groupoid, up to this it is semigroup, and up to this it is monoid. Okay. So, now we define, now we will move to the definition of the group. So, before that, let us just define what is called cohesive group. So, cohesive group, this is the definition of cohesive group. Okay. So, a groupoid G is said to be, this is the definition, is said to be cohesive group if for any two element A B if for any two elements A B belongs to G, each equation equations like A star x equal to B and x and y star A is equal to B has a unique solution. So, that means they are the has a unique solution, then it is called a cohesive group. Okay. Now, if it is, say, if we take this to be E, B to be E, then this will be happen to be the inverse. So, from here we can feel of concept of existence of inverse. Now, we will finally move to the defining the group of group. So, now we going to define the group. So, this is definition. Okay. So, let G be a non-empty set and this is a binary operator. Binary operator on G. need not be closer. So, it is a function from G star G to, if it is closer to G, otherwise it is to some other set, is called a group if the following condition satisfied. If and only if first condition is closure, A star B belongs to G, this is the closure property. That means, it must be a groupoid. So, this must be a groupoid. A star B is equal to A, so this must be closure. Then it must be associativity. A star B star C is equal to A star B star C. This is true for all A B C. So, these two will give us, this is the associativity property, associative. And the next one is existence of identity. So, there must exist an element E from G such that A star E is equal to E star A is equal to A, and this is true for all A. So, this is G. Okay. So, this is the existence of identity. So, this is the identity element, and last one is the existence of inverse. So, for every element has a inverse. So, given a let A belongs to G, then there exists a B such that A star B is equal to B star A is equal to E. So, this is the existence of inverse. So, this is the inverse. Okay. So, every element has a inverse. Every element has a inverse. So, this given a element A, we must have a element B such that A star B is equal to identity, which is same as B star A. So, this is telling us every element of G has a inverse. So, if this so up to this it is a semi group. Semi group means closure and associativity. Now, if we have existence of identity, then it is called monoid, and then if we have existence of inverse, then along with that, if we have also existence of inverse, if for every element we have inverse, then it is called a group. Okay. So, this is the property of, this is the definition of a group. So, every group has this many properties, this basically 4 properties. If these 4 properties satisfy, then we call this G along with this algebraic structure is called a group. Okay. If these 4 properties satisfy. Now, when we call this is a commutative group. So, for group we just need this 4 property: closure, associativity, closure. That means, if we take any 2 element, if we operate this by operation, it must belongs to G. Associativity, A star B star C is B star A star B star C. Associativity, existence of identity, we must have an element which is called identity element, such that if we operate with any other element with the identity element, it will give us that element A. And existence of inverse, for every element in A, there must exist the corresponding B such that A star B is equal to B star A is equal to the identity element. So, these 4 properties are the properties of a group. Now, when we called a group to be abelian group, if along with this, if we have another property, 5th property, which is commutative property, if we have if the star is commutative, then along with this 4 property, this will called a commutative group or abelian group. Abelian group. So, that means for abelian group, first of all it has to be a group by these 4 properties, and then the star must be, that operator must be a abelian operator or the commutative operator. Then it will be called a commutative group or abelian group. So, this is the definition of a group. Now, in the next class we will discuss some properties of a group and we discuss some of the example of the group. Thank you.